Okay, this is the video for practice exam 2. First question is, label R as stereochemistry. So first, let me just label that there are two stereogenic centers. This one here, this is going to be 1. There's these 2 carbons here. This one has a fluorine on it. This one has 3 carbons. Fluorine has a higher atomic number than carbon, so this is going to be 2, 3. It's going to go this way. It's going to look R, but again, the 4th priority group, the hydrogen, is wedged. So this is actually S. Do this one. For this one here, fluorine's going to get 1. This carbon has a bromine attached to it, so it's going to be 2. This is going to be 3. You can go this way. It's going to look S, and it is S. This is SS. All right, for this one, you just have this one chiral center right here, and now we got 3 carbons. So I'm going to name these C1, C2, C3, right? When we compare these, C1 has 2 bonds to oxygen and 1 bond to carbon. C2 has 3 hydrogens, and C3 has 2 bonds to oxygen and 1 hydrogen. So, priority group 1 is going to go to C1. Priority group 2 is going to go to C3. Priority group 3 is going to go to C2. And so this is going to go 1, 2, 3. It's going to look S, but it's actually going to be R. All right. Just a quick refresher. And remember, you should also make sure that you can do one where the 4th priority group is in the plane and how to do the switch method. Make sure you know how to do that too. That's something that showed up on your quiz. So make sure you can do all the things on the quiz. Okay, next problem. Determine the relationship between the following molecules. So I always like to change my Newman projections into bond line structures, and because the OH and F is on the left, right? These are the 2 important carbons. I'm going to look at this from the left, and I'm going to say OH up, the CH3 is down. I'm looking at it from the left, so what's left is going to be dashed. And then on the right, those hydrogens are going to be wedged. Okay, now I got this drawn out. I can do RS stereochemistry to determine these, so let me just do this quick. Fluorine is going to be 1, oxygen is going to be 2, this is going to be 3, it's going to go this way, and this is going to be S. And for this one, it's carbon, carbon, carbon. The fluorine one is going to be 1, so let me switch this color. So 1 for over here, 2 towards the nitrogen, 3 here. And you can break it out if you want. I'm just in a rush because I don't have a ton of time to do this. So it looks R, but this is actually S. So SS. All right, now let's look at this one. Use the same colors. So fluorine again is going to get 1, oxygen is going to be 2, this is going to be 3 right here. Right, so this is going to go 1, 2 to 3. It's going to look R, but actually be S. I'll do the green ones for this one. Again, we've already determined this is 1, 2, 3. Hydrogen's 4, but I'm not going to number it because it doesn't get included in the circle. Oh, you cannot see that very well. All right, so it goes 1, 2, 3. It looks R, but this is actually S. So these are same molecule or identical. All right, for these right here, I'm going to do this a different way, which is that this CH3 is in the same place as this CH3 in the front carbon. So I'm just going to rotate the back carbon, and instead of doing RS stereochemistry, just to do something different, which you can draw both of these, just like I switched this one to a bond line structure. You can switch both of these and determine it with R and S, and that's perfectly fine if you want to do it that way. But I understand that not everyone's doing it that way, so I'm just going to do this another way, which is I'm doing it based off of mirror images. So I'm going to keep the front carbon in the same place, and I'm going to bring this hydrogen all the way around to here so that it lines up with this hydrogen. This is going to have this left side be the same on both. So when I do that, that's going to get me to front carbon being the same, so I'm not touching it. The back carbon, let's see, and that comes all the way over here. That means everything's going to be the opposite side where it used to be. This also brings the bromines together. So notice how the bromines were together here. Now they're up here. Now, when I have this, right, these are in the same place, but the stuff over here and the stuff over here is switched. on both the front carbon, right? HBr, BRH, CH3, BR, BR, CH3. I can't see that very well. They're switched on both the front carbon and on the back carbon. Maybe I can move this over a little bit more. Let's see a little bit more on the page. Hopefully this tower of books does not fall. Right? Meaning both stereocenters are switched. Remember, when you switch two groups, you switch the stereochemistry on that. So on the front carbon, we see the H and the Br are switched. Two groups are switched. So this one's going to switch, be the opposite. On the back carbon, we also see two groups are switched, Br and this. So these are enantiomers. I don't think there's an N here. I think there's no N there. Sorry. Enantiomers. I think that's what it's called. I'm having second guesses. Okay, for this one, we have a methyl group on carbon number 3 versus having one on carbon number 2. So these are constitutional isomers. Remember that for alkenes, you cannot have enantiomers. You can have diastereomers, you can have constitutional isomers, and they can be the same. These are constitutional isomers because I ripped off of carbon 3, and would have to put it on carbon 2 to get to this one right here. Good. All right. Next question. Draw the major product. It's basically doing a lot. So let's do mechanism. We have a tertiary alkyl halide, and we got methanol and heat. So this is going to be an E1 mechanism. I encourage you to write down the mechanism for all of these, just so that you're used to knowing what the mechanism is so you don't get lost. And then I'm going to do these through the mechanism, and I'm going to abbreviate the benzene ring pH just to make it simpler. And then I am going to get a hydride shift because secondary allylic is more stable than tertiary. And then, of course, the lone pair is going to deprotonate this and get us our final product. There's no E and Z in this, so there's just only one product for this. Good. All right, next one. This is a strong nucleophile weak base. So this is going to be not E1, SN1. Right? That's what we have for that if you look at that strong nucleophile weak base. So the first step is going to be this leaves. You ask yourself, do you have a carbocation rearrangement? This is tertiary. You can't go from tertiary to secondary, so there will be no ring expansion. You can't do I had somebody ask me yesterday, which was Tuesday, right, if I could have a ring expansion from here to here and get from 4, 5, 6, 7 member ring. No, you can't. You can only expand one carbon. So the next step of this is going to be taking this S minus, coming here. 1, 2, 3, 4, 5, S. CH3, and getting this as my major product. No rearrangements in this. Okay, this is a strong nucleophile weak base and a secondary, so this is going to be SN2. And the way this is going to work is you're literally going to do this and just do your SN2 here. You get inversion of stereochemistry, but stereochemistry is not shown here, so you don't have to show it here. If it was shown there, like this is going to be 50% R, 50% S. That's the way that's going to be. If it was shown here, you'd have to show it, but since it's not, Okay. Secondary alkyl halide, strong base, strong nucleophile. It looks like it's going to be E2, but there's no anti-periplanar hydrogens in this molecule, meaning E2 is not possible. But if you remember, SN2 is a minor product in this. So if E2 is not possible, then the actual mechanism is going to be SN2. Of course, you invert the stereochemistry for it. So there, that's that problem. Okay, next. We're going to have this. This is going to be an E1 because weak base, weak nucleophile, and heat. So have the chloride leave. If you're not comfortable using that chart with the different types of bases and nucleophiles, yeah. If you're not comfortable using that chart and being able to predict quickly like what the mechanism is, you need to keep practicing and practicing and practicing before the exam so that you can do that. Right, we're gonna get a ring expansion. It's a secondary, you can make it more stable. Whenever you have a carbocation, you always look to see if you can make it more stable. In this case, you can by a ring expansion. I try to keep these carbons over here on the edge consistent. So this is gonna be 5, 4, and 3. And this will be 6, 2, and 1. On carbon 2, I'm gonna have a methyl group. On carbon 1, I'm also gonna have a methyl group. And the charge always goes to carbon 2. And then I'm gonna have water. This as your product. Good. All right, next one. This is minus plus, so this is a strong base, strong nucleophile, secondary alkyl halide. This is going to be E2. Now, it looks like there's no anti-periplanar hydrogen here, but remember you can do bond rotation to get it there. But in fact, these are two methyl groups, so if you just did this and you got this, there's no E and Z for this alkene. So whether or not you did the bond rotation, which you could do, you would always get this. So I'm not going to do it just because of time, and this is a long exam, and I don't have a ton of time or space on my iPad to do that. So this is cold. It's going to be SN1, weak base, weak nucleophile. Remember, it's not reactive with a primary alkyl leaving group, so there's no reaction with this, but there is a reaction here. So this is going to be this, get a hydride shift. I'm really just worried about how long those IR problems are going to take at the end. This common attack. That's the product there. All right, last on this page, which is a strong, very strong nucleophile. It's an E2, and you have to know which way to eliminate. So I have a small base. I don't have TP toxide, so I want to make the most substituted one. So I need an anti-periplanar hydrogen. That's this one right here. I also have one on this methyl group too, but that's would give me the least substituted one. This one here is not anti-periplanar. So the way this is gonna work is this is gonna come, grab that hydrogen and kick off the bromine. All at the same time, because that's the way E2 works. You're gonna get this like that. So the product there. All right, and we got more. All right, MBS and light. Remember, this puts a bromine at the most stable radical position, and this MBS is used because if you have an alkene, you need to use it. So basically, if I go through the mechanism, I'll pretend initiation already happened, right? You're gonna get this bromine. Good. All right, next one. This one's just Br2 and a peroxide, so usually you'll have heat that'll come with it, which I probably should have put. But if you see peroxide or light, you know it's a radical reaction. And this one, of course, is going to, I guess I should do this. Radical Br, just so that you have all the mechanisms here. Good. You get that. Cl2 in light. Again, you're going to have your Cl radical It does not matter which hydrogen you pick because they are all this equivalent by symmetry. Actually, if you drew 6 products here, I would probably take half a point off your exam, just because you didn't understand that they were all the same by symmetry. Right? It just demonstrates a lack of knowledge. So you should know that they're all the same. And it's very difficult to have these reactions. Yeah, so Cl2 reactions to be useful. All right, SOCl2 excess. Remember, this does an SN2, so it's not going to do anything with a tertiary alcohol, but it will do something with this. And you don't need to know the mechanism, so this is one of the ones I'm not going to draw the mechanism. I'm just going to draw the product, which should be this. PBr, again, is the same. This is going to be no reaction because, again, it's a tertiary alcohol. You don't react PBr3 or SOCl2 with tertiary alcohols. Okay, now we get to the IR section, which I'm going to try to spend a little bit more time on and not move quite so quickly. So, what I want you to be able to do basically with this first question is look at a molecule and know what types of peaks you're expected to see, which would be like a C double bond O at approximately 1700 reciprocal centimeters, C double bond C, which would be at approximately like 1650-ish, and then NH, which would be approximately like 3200, right? The point of this, I know you can look it up on the chart and you can see all these absorbances, and that's fine, but I want you to be able to look at the molecule and know like what you should be looking for. If you get a multiple choice, we have an IR spectrum, you have to pick which molecule fits it, right? You should be able to look at that and say, I'm looking for these peaks, and that's what I want you to see. So again, this is going to be at like 1700, maybe a little bit more than, usually a little bit more than 1700 for the carbonyl. C triple bond end is about 2200, I think. Right? So that's what I want you to be able to do. Real quick problems, but I want you to be able to do that. Okay, now doing this IR. So first thing we have is we want to do our degrees of unsaturation, and you completely ignore the oxygen for it. Now, I forget what the formula is that we use in this class because I learned a different formula when I was an undergraduate, and I can get the degrees on saturation, and so I don't want to be confusing. So use the formula, figure it out, but I will tell you that this is going to be degrees on saturation is going to be equal to 2, right? Yeah. I learned a mathematically equivalent formula, but it's different. And I can never keep it straight which one they use here. So, now, in the IR spectrum, I see I have a C double bond O, I have a C double bond C, that's 2 degrees on saturation. This looks like an sp2, right? If I draw this line from like 3000, right? Sort of like that. This is sp2CH, sp3, CH, right? And so in this box, I'm supposed to draw a molecule. I have 6 carbons, 10 hydrogens, and then an oxygen, right? So, I can do like fragments if I want and just say, look, these squiggly lines mean rest of the molecule. I know I have to have at least one H, and then there are 3 other carbons I can stick around. So, why don't I just do this? Why not? 1, 2, 3, 4, 5, 6. You just have an alkene and a ketone, and that's a molecule that fits. There are a whole number of molecules you can hit. As long as there's a ketone and a alkene, that'd be good. You just don't want to have, I'd be okay if you did this, but technically this would not be correct, have this type of structure because this makes this carbonyl show up below 1700, so it'll be like 1695 or something like that, versus this one, if you look, it's actually like the numbers given right here, 1718. So that's the only one you shouldn't draw, but any other one will work. All right, next one, C6H10O. Again, so the degrees of unsaturation is again going to be 2. It's the exact same formula as before. I see I have an OH right here, so that uses up my oxygen. And I have this peak right here, which is at, what is this number at? It looks like it's at like 1713. It's at a weird number. So I'm not sure what this is, but it can't be a carbonyl if I already used up my oxygen. This is a clear carbon or alcohol peak. Carbonyl peaks, you normally come all the way down here. So I don't know what this peak is doing here. It may or may not be important. We got 2 degrees in saturation. And then I got this little peak here. That's about it, I don't know. Maybe like 22. Is that like 2200? So I think this molecule either has 2 rings in it, or it has an alkyne in it. I don't know if this is the alkyne. It might be an alkyne. So this may be that, but if it was on an exam, you'd have a better peak than this, or a flatter baseline. We definitely have an alcohol, and we definitely have sp3 CHs. So if we have an alkyne, it's an internal alkyne. It does not have an SPCH. So let me just, from where I am, draw some like potential molecules. 4, 5, 6, I guess. I put an alcohol any which way, right? The other thing I can think of is I need 2 degrees on saturation with rings. So maybe with only 6 carbons, right? Because you need 2 degrees on saturation. That seems crazy, but there's no alkene, no visible alkene. I think this is ignore this. So I think this is the right answer. I think it's an alkyne. I'll just take the alcohol here, right? So not this one, too many ring, or too strained. Not a very likely compound, right? But I mean, if you want 2 rings with 6 atoms, you'd have to do something like that. So ignore this peak, and we'll do that. Next one. Okay, this is still degrees on saturation equal to 2 because it's the same molecular formula. In this one, though, we have a carbonyl. A little peak there. I don't know if that's important yet. This looks like our sp3 CHs, which I would definitely label if you had to label something in the spectrum. This looks like an aldehyde CH. So it looks like this bond right here. So that's 1 degree of unsaturation. Do we have another one? I don't think that these look really small, I think I'll ignore those 2. So then our other degree of unsaturation better be in a ring. I can't do a 6-membered ring, you can't have an aldehyde. Let's do like a 5-membered ring. No, hold on. Let me think. Maybe this peak is important. So maybe this is the CC. Maybe we have an alkene. Oh, okay, I understand. So this is 1695. It's below 1700. That means that it is a carbonyl right next to a CC double bond like this. And we know this is an aldehyde from the CH peak here. Now that I have this, you can basically just stick the other 3 carbons anywhere you want. So this is the structure. And the reason I know I have this is because this is slightly below 1700. So if you look at the bottom of your IR table, there's like a little footnote that says something about these carbonyls showing up at like 1690 something or minus 30 reciprocal centimeters or wave numbers, right? So that's how I know I have this, is by this being a carbonyl and it showing up right below 1700. Okay. Whew. So I get nervous. I can't remember to do it. These I learned afterwards that like Dr. Hirschauer saying you how many carbons there are. So there are, let's see, 6 carbons plus in D 13 hydrogens. All right, if you ever have an odd number of hydrogens, you know you need to have at least an odd number of nitrogens in the molecule. So this is like 116 m plus 1. So m is equal to 115. All right, we take our 115. We have 6 carbons, 72 minus, this is 3, 4, 13 hydrogens. It's going to be 30. All right, we have an odd number, so let's assume we have 1 nitrogen, 16. So then we have 1 oxygen, right? So this is nitrogen, this is hydrogen, this is carbon, oxygen. So our formula is going to be C6H13NO. Right? Now we can do degrees on saturation, and when you see it, it's going to be equal to 1. Yeah. So I'll let you do it on your thing, but the degrees of unsaturation is going to be equal to 1. Right? Now we look at our thing here. This looks like an NH bond. These are sp3 CHs. I don't really see anything of importance in this area here. I don't think I count on that. This could be an alcohol. underneath kind of getting merged in with that NH and not very good resolution. So I'm guessing you have a ring. And also the other reason I don't think that you have a alkene is that there's no sp2CHs for sure, and that seems really small. I don't know how I would count on that. So let's do a ring and do something like this. Just something like that. Actually, I know why this is, yeah. So this is the right compound, and I know why this looks so messy. It's because this OH can hydrogen bond with this NH2, and that's why this kind of looks messy there. All right, next one. So we're here, this is 99 here. This is 100, there's one there, the M plus one. So M is equal to 99. Carbons is equal to 6. Hydrogen is equal to 13. So, all right, 99 minus 72 is the C's. So it's 27. 13 minus is going to be 14. 14 minus, which is the N, 0. Remember, it's an odd number, so we only have one nitrogen. Okay, so we have this C6H13N. This is our molecular formula. This is a characteristic NH. sp3CH is there. And we have no carbonyls. Oh, degrees on saturation, I'm sorry. It's also equal to 1. It's the same formula as last time. So, no carbonyls. I think, again, this is going to be a ring. That is not like, that is not a C double bond. Not CC double bond. And the reason why CC double bonds tend to be very sharp like this, very, very sharp, because that broadness usually comes from hydrogen bonding of some sort. And CC double bonds kind of hydrogen bond. So, we got 6 carbons. Let's just draw a ring and put an NH2. You can draw a 5-membered ring and put a CH2 and then NH, or a methyl group and an NH2, whatever you want to do. Right, but you should have an NH2 in this. So, good. Okay, I think this is the last one. Oh boy, I should have blown up this area down here. 75, 6, 7, 8, 9, 10, 11. So maybe this is 181. And this is M plus 1. There are 2 peaks that look like they have a bromine in it. So I think this is 178. And this equals this. This is M plus 3. I think. So I think there are 2 little peaks there that you can see that have that there. Alright, if it's 178, how many carbons is this? So carbons